Hi, my name is Michael Benazes. This is Math 231 Linear Algebra Final Review. So this video is to prepare you for the final. We're going to go over the practice problems on the sheet I gave over you. Keep in mind that the final you're going to take is not exactly this final. It's not going to be 2 hours long. It's not going to be these questions. It's going to be different questions, different number of questions possibly. And so be prepared for anything that we learned in this semester. But this is a good practice because it's 10 questions that covers material throughout the course from beginning to end. Okay? Let's go. So the first problem on the test is find the characteristic equation, the eigenvalues, and bases for the eigenspaces of the matrix. And so here the matrix is the matrix A, which is this matrix. Okay, so you have this matrix, and you want to find the characteristic equation of that matrix. And so the characteristic equation you get by the equation determinant of lambda I minus A is equal to 0. Okay, so you want to express that equation in a simple way. Okay, so the determinant of lambda I minus A is equal to 0. So the determinant of lambda I minus A is the determinant of this matrix, where you take the negative of each entry there and you add lambda to the main diagonal entries. Okay, so you're just taking the negative of everything there and you're adding lambda on the main diagonal entries. And so that's the determinant of lambda I minus A, and it's equal to 0. So take the cofactor expansion along the first row of that matrix. The cofactor expansion along any row or any column of a matrix is the determinant of that matrix. And so we're going to find the cofactor expansion along the first row, and that will be the number you get is equal to the determinant of that matrix by definition. And so the cofactor expansion along the first row of that matrix, you get this. Okay, so you should know how to find the determinant of the matrix. And so this involves a lot of tedious calculations. And so if you make a mistake on the calculations at any point, it will give you the wrong characteristic equation. Okay? And so you may get stuck in this problem because you make a calculation mistake somewhere in all of these calculations. So you have to make sure all of your calculations are correct when finding the determinant of this matrix. Okay? And so you define the determinant of each matrix by, by the method that's illustrated by these arrows, right? This times this minus that times that, this times this minus that times that, this times this minus that times that. That's how you calculate the determinant of these three 2x2 matrices. Okay? And so that method is for only 2x2 matrices. So the brackets, I'm going to put the determinant of each matrix. And so I'm going to do some of the calculations, but most of them I'm going to leave undone. So I'm just going to write down. But here, -3 times -6 is 18, and you're going to subtract the product. So I'm subtracting 18 there. And so I'm going to just have to skip some of the calculations here because it's just easier to present that way. Okay, so it's this times this, which is -18, minus this times that, which is +6 times that. Okay, so now simplifying this further, this is lambda minus 1 times lambda squared plus lambda minus 2. This is -3 times -3 lambda minus 6. This is -3 times, this is 6 lambda here, not 36, this is 6 lambda here, and then there's a 30 minus 18, and that's a plus 12, and that's equal to 0. And so we keep going, and so this times this, you get lambda cubed plus lambda squared minus 2 lambda minus lambda squared minus lambda plus 2 plus 9 lambda plus 18 minus 18 lambda minus 36 is equal to 0. So we're going to simplify this now. There's a lambda cubed here. We use another marker. There's lambda cubed. The lambda squares cancel. We get a minus 2 lambda, minus 3 lambda, 6 lambda, minus 18 lambda. That's minus 12 lambda. So far everything looks good. There's a 2 and 18, that's 20. 20 minus 36 is minus 16. And we get the characteristic equation lambda cubed minus 12 lambda minus 16 is equal to 0. That's the characteristic equation for that matrix A. Okay? Okay, so I'm going to erase the calculations here that got me the characteristic equation. Okay, so now next, now that we have the characteristic equation, the next thing to do is find the eigenvalues. And to find the eigenvalues, we're going to factor the characteristic polynomial into linear terms, and then we'll be able to find all the solutions to the equation easily from that. Okay, so so when you have a polynomial like this, since this last term is a negative 16 and this is a positive 1, you know that all the fractional solutions to that equation are fractions where the numerator is a number that divides negative 16 and the denominator is a number that divides positive 1. Okay, so the denominator could be plus or minus 1, and the numerator could be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, or plus or minus 16. And so those are all the possible fractions that could be solutions to that equation. Now, of course, there could be solutions that are not fractions. But if a fraction is a solution to this equation, it has to be of that form. But anyway, actually, you can just kind of go by instincts a little bit here. If you look at plus or minus 1, plus or minus 2, maybe one of those will work. And so if you look at negative 2, plug in negative 2 into this equation. What you're going to get is negative 2 cubed. And so you see this through practice, right? If you took, when you took pre-calculus, you practiced this. And so that's where this skill comes in handy. Negative 2 cubed is negative 8. Minus 12 times negative 2 is plus 24, and then minus 16. And if you add those up, you get 0. And so what this shows is that this equation has a solution of lambda equals negative 2 is a solution. So that implies lambda equals negative 2 is a solution to that equation. You can plug in negative 2, and both sides are equal to each other. And so if lambda minus equals negative 2 is a solution, that means lambda plus 2 divides that polynomial on the left side. So I'm going to divide that polynomial by lambda plus 2 because lambda equals negative 2 is a solution. And so I'm going to divide that polynomial by lambda plus 2. Okay, I'm going to do long division. And so you have lambda squared here. Lambda squared times lambda is lambda cubed. Lambda squared times 2 is plus 2 lambda squared. I'm going to subtract here. And the lambda cubes cancel. And you get negative 2 lambda squared minus 12 lambda minus 16. Then the lambda here times minus 2 lambda. Negative 2 lambda times that would give you minus 2 lambda squared. Minus 2 lambda times positive 2 would give you minus 4 lambda. And then when you subtract the 2, then there's minus 8 lambda minus 16. And if you do minus 8 there times that, you get minus 8 lambda minus 16. And those cancel and you get a remainder of 0. And so lambda plus 2 times lambda squared minus 2 lambda minus 8 is equal to that polynomial by long division. Okay, so factoring this, you get lambda plus 2, we need a new marker, okay, you have lambda plus 2 times lambda squared minus 2 lambda minus 8 is equal to 0. And so now we can further factor this. This is just lambda minus 4 times lambda plus 2. And then you still have the lambda plus 2 there. Okay. This is lambda minus 4 times lambda plus 2 because minus 4 lambda plus 2 lambda minus 2 is lambda, and minus 4 times positive 2 is minus 8. And you have the lambda times lambda, which is lambda squared. Okay, and so you now have lambda minus 4 times lambda plus 2 squared is equal to 0. That means the only solutions, the only eigenvalues that we have are lambda equals -2, which we had already, and we have lambda equals 4. So lambda equals -2 and 4 solutions. And so I mentioned before that the only fractional solutions would be denominators plus or minus 1, numerators plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. And so 4 falls into that character, and 4 is a fraction 4 over 1. And so you would have 4 here, and the 1 there, 4 over 1, 4. Okay, so lambda equals -2 and 4 are the only two solutions to that characteristic polynomial. So we have all the eigenvalues. And the third thing question when asked for is find the bases for the eigenspaces of the matrix. Okay, so find bases for the eigenspaces of the matrix. And so we have two eigenspaces, right? One corresponding to each eigenvalue. And so let's find the eigenspace corresponding to each eigenvalue of this matrix A. Okay, so we already have lambda cubed minus 2 lambda minus 16 is equal to 0. That was the characteristic equation. And -2 and 4 are the eigenvalues. Okay, those are the two eigenvalues, -2 and 4. Okay, so let's find the eigenspace corresponding to lambda equals 4. And so the eigenspace corresponding to an eigenvalue are all the solutions to lambda I minus a times x is equal to 0 for that chosen value of lambda. So in this case, it's the general solution to 4i minus a times x is equal to 0. It's all the vectors x that satisfy that equation. That's the eigenspace corresponding to lambda equals 4. So lambda I minus a, 4i minus a is plugging in a 4 into that matrix. And so we're going to plug in 4 here. We're going to get 3, 3, -3. -3, 4 plus 5 is 9. -3. You get -6, 6, and 4 minus 4 is 0. So that's 4i minus a. And then I'm just going to write the augmented matrix corresponding to that linear system that's represented by this matrix equation. So this matrix equation represents a linear system. This is the augmented matrix corresponding to that linear system. We're going to get this augmented matrix to reduced echelon form, and we're going to use that to find all the solutions x that satisfy that matrix equation and all vectors x that satisfy the linear system corresponding to this augmented matrix. Okay, so we're going to get this to reduced echelon form. I'm going to multiply this by 1/3, get 1, 1, -1, 0. I'm going to take 2 times this row and add to that one. And so this is going to be 0. This is going to be 12. And that's going to be -6. And that's going to be 0. I'm going to add this row to this row, and it's going to be 0. That's going to be 12. And that's going to be -6. And that's 0. Then I'm going to, I'm going to take -1 times this row and add to that one, and I'm going to get all zeros in the last row. I'm going to multiply this row by 1/12 and get 0, 1, -1/2, 0. Then I'm going to take -1 times this row and add to that one. And then I'm going to get -1/2 here, and that'll be a 0. Okay, so then now if you let the matrix vector x be x1, x2, x3, then x1 and x2 are leading variables, x3 is a free variable. So x3 is going to equal t, x2 is going to equal 1/2 t, and x1 is going to equal 1/2 t. And so the vector x, which is the vector x1, x2, x3, looks like the vector 1/2 t, comma 1/2 t, comma t. That's equal to t times 1/2, comma 1/2, comma 1. And so any multiple of 1/2, comma 1/2, comma 1 is a solution to 4i minus a times x is equal to 0. And so a basis for that eigenspace is the basis is the basis containing the single vector 1/2, 1/2, 1. That's a basis for the eigenspace corresponding to lambda equals 4. Okay, so our next integer is that the basis corresponding to lambda equals 4, one basis is 1/2, 1/2, 1. Okay? And now let's find the basis corresponding to lambda equals -2. Okay, so we're going to find the eigenspace, a basis for the eigenspace corresponding to lambda equals -2. And so that would be -2i minus a times x equals 0. Well, the general solution of that equation would be the eigenspace corresponding to lambda equals -2. And so we're going to write the augmented matrix corresponding to the linear system that's represented by this matrix equation. I'm going to plug -2 in here, and I'll get -3, 3, -3, 0, -3, 3, -3, 0, -6, 6, -6, 0. Okay, so I'm going to take -2 times this row to get to that one. And so I'm going to get 0 here, I'm going to get 0 here, I'm going to get 0 there, and 0 here. I'm going to take -1 times this row and add to that one. I'm going to get 0 here, 0 here, and 0 there, and 0 there. And I'm going to take this row and multiply it by -1/3. I'm going to get 1, -1, 1, 0. Okay, so this matrix in reduced echelon form is that. This augmented matrix in reduced echelon form is that. And so here's leading 1. And so x1 is a leading variable. x2 and x3 are free variables, so I set a parameter equal to each of them. x2 is going to be t, x3 is going to be s. So x1 is then equal to x2 minus x3, which is t minus s. Okay, so a vector x in this eigenspace corresponding to lambda equals -2 is the vector x1, x2, x3. Well, that's equal to t minus s, comma, t, comma, s. This is equal to t times 1, 1, 0, plus s times -1, 0, 1. That's the all vectors of that form are all the solutions to that linear system, which is the eigenspace corresponding to lambda equals -2. And so a basis for this eigenspace is the basis consisting of these two vectors. They're linearly independent, and they span the basis. They span the eigenspace. Every solution is a linear combination of these two, so these two vectors span the eigenspace, and they're linearly independent. Okay, they're both non-zero, and neither is a scalar equal to the other, and so those two sets form a linearly independent set. Okay, so it forms the basis for the eigenspace, and so a basis for this space, I'm going to call that B2. B2 here is going to be the basis for the eigenspace corresponding to lambda equals -2, and that will be the set containing the two vectors 1, 1, 0, and the set -1, 0, 1. And so we have the two bases here. This is the basis for the eigenspace corresponding to lambda equals -2, and this is the basis corresponding to lambda equals 4. And so that's number 1. Okay? That's the characteristic equation. These are the eigenvalues. This is the basis for the eigenspace corresponding to lambda equals 4, and this is the eigenspace corresponding to lambda equals -2. And we're done with number 1. Okay, number 2. Okay, so number 2 on this practice final is use matrix multiplication to find the image of the non-zero vector -3, 17 when it is rotated about the origin through an angle of theta equals 120 degrees. Okay, so the matrix we use for a rotation about the origin through an angle of 120 through an angle of theta is this matrix. The first column is cosine theta, sine theta, and the second column is negative sine theta, cosine theta. Okay? Okay, and so this is the matrix. We left multiplied by a vector by this matrix, and the result is rotating the vector by theta degrees counterclockwise about the origin. So in this case, we're going to take the vector negative 3, 17, and left multiply it by that matrix where theta is 120 degrees. And so this is going to be cosine of 120 degrees, sine of 120 degrees, negative sine of 120 degrees, and cosine of 120 degrees. Okay? So I just plugged in theta equals 120 degrees into that matrix. Okay? And so now this is now equal to that cosine of 120 degrees is negative 1/2. And then sine of 120 degrees is root 3 over 2. And now negative sine of 120 degrees is just negative root 3 over 2. Negative of that, which is negative root 3 over 2. And cosine of 120 degrees is still negative 1/2 from what we calculated over there. So then that's that matrix, and you just multiply that by negative 3, 17. And so then what you get is, this is a 2 by 2 matrix. This is a 2 by 1 matrix. And so the inner entries are the same, the outer entries determine the size of the matrix. So the resulting matrix is a 2 by 1 matrix. 2 rows, 1 column. So the first entry here would be negative 1/2 times negative 3, which is 3/2. 3/2 plus this times this. So it's 3 minus 3, it's 3 minus 17 root 3 over 2. Okay, and you could leave it in radical, you could leave it like that. Okay, and then this times this plus this times that, you get negative 3 root 3 minus 17 over 2. Okay? Okay, and so that's the answer. So if you rotate the vector negative 3 comma 17 about the origin an angle of 120 degrees counterclockwise, you get the point 3 minus 17 root 3 over 2 comma negative 3 root 3 minus 17 over 2. Okay, and that's the answer to number 2. Okay, so continuing to number 3. So for number 3, we're going to evaluate the determinant. And so this is an easier problem than the last two. So actually, but number 2 is very easy if you know the formula already. So if you have the formula memorized, that can be a very easy question. You're just plugging in. So okay, so you find the determinant of this, and so you can just find the cofactor expansion on the first row. And so that's equal to 3 times the determinant of the corresponding submatrix, the determinant of that, minus this entry, negative 1, times the determinant of that submatrix. If you have trouble finding this cofactor expansion, I welcome you to continue to write everything out like I did in the beginning of the semester. Okay, if it's not clear how to write all this out, you can do the best thing to do is to write each step in and not to, write everything that I told you to do. Okay, and it's plus negative 2 times the determinant of corresponding. That's 2, 5, 2, 3. Okay, and so now we have that 3 times that minus negative 1 times the determinant of that plus negative 2. Okay, so now this is equal to 3 times the determinant of that, which is 35. 35 minus negative 9, which is 35 plus 9, which is 44. Okay, minus negative 1 is plus 1. So that's plus the term to this, which is 14, minus negative 6, which is 20. So that's plus 20. And then plus negative 2 is minus 2 times the determinant of that, which is 6 minus 10, which is negative 4. That's equal to 0. So this is equal to 3 times 44, which is 132. And then plus 20. And then minus 2 times minus 4 is plus 8. And not equal to 0. Sorry, it's not equal to 0. Okay, so we're just finding the determinant of this matrix. And so that's equal to 132 plus 8 is 140, 140 plus 20 is 160. And so the determinant of that matrix is 160. Okay, and so that is number 3. So next is, we're going to do number 4. If you're stuck on a question during the final, you can skip it and go back to it, right? So you don't want to use all the time on the test for one question if you're stuck on it. Keep that in mind. Okay, so number 4, find a basis for the solution space of the homogeneous system and find the dimension of that space. Okay, so we want to find a basis for the solution space of this homogeneous system. So you have the system written out on the page there. I'm going to go right to the corresponding augmented matrix for that linear system to save space on the board. Here, okay? So this is the corresponding augmented matrix for that linear system. Okay? So we're just writing things out using matrices instead of writing the linear systems. That way it's less work. You have to write less to do the same thing. Okay? So here's the corresponding augmented matrix, and we're going to get this to reduced row echelon form in order to find the solution space of that system. Right? It's a homogeneous system because each equation is equal to 0. That's what a homogeneous linear system is. Okay, and so let's get this to reduced row echelon form. Let's take the first row and add -1 to it to the second row. So -1 times the first row, add to the second row. I'm going to keep the first row exactly the same. So -1 times this row plus that one, you get 0, 1, 2, 3, and that's 0. -2 times the first row, added to that, and you get 0, 0, 1, -3, and that's a 0. Now I'm going to take the first row and add to the fourth one and get 0, 0, -3, 9, and then that's 0. Okay, so continuing, I'm going to continue over here. I'm then going to take 3 times this third row and add to that. So I'm going to keep the third row the same. I'm going to add 3 times that to this row. Get 0, 0, 0, 0. There, and the 0 at the end. I'm going to take -2 times this row and add it to that. And so I'm going to get 0, 1, 0, -2 times this row and add it to that. And so I'm going to get 1, 0, 9, and 0 there. Then I'm going to take -3 times this row and add it to that row. I'm going to get 1, 2, 0, 11. Okay, and I'm almost done because there's only zeros above this leading one, but there's a 2 above this leading one, so I have to get rid of this 2. So I'm going to take this row, multiply it by -2, and add to that first row. And so the fourth row is going to be all zeros. The third row is going to stay the same. The third row is going to stay the same. Now the first row, I'm going to take -2 times this row, add to that one. It's going to be 1, 0, 0. -2 times this is -18. -18 plus 11 is -7. You get -7. Okay, so x1, x2, and x3 are leading variables because they correspond with leading ones there. So x4 is the only free variable because it doesn't correspond to a leading one. And so as a free variable, you set equal to a parameter, let's say t. So x4 is 3, x3 is 3t, x2 is -9t, and x1 is equal to 7t. And so, okay, so actually, sorry, it's not x4, x3, it's w, just t, z, which is 3t, y, which is -9t, and x, which is 7t, okay? So a solution, a solution to this homogeneous system is of the form w, x, y, z. I mean, x, y, z, w. And what that's equal to right here is negative 7t comma negative 9t, 7t comma negative 9t comma 3t comma t. That's equal to t times 7 comma negative 9 comma 3 comma 1. Okay, so any real multiple of 7, negative 9, 3, 1 is a solution x comma y comma z comma w to that linear system. So a basis to this linear system is the set containing the one vector 7 comma negative 9 comma 3 comma 1. That's one basis. That's a basis for that for the solution space of the homogeneous system. And so since this basis contains exactly one vector in it, that means the dimension of that space is 1. So the dimension is 1 for the solution space of the homogeneous system. The dimension of the solution space of the homogeneous system is 1. And we're done with number 4. Okay? That's number 4. We found a basis and we found the dimension. Okay, so let's keep going. So after number 4, we have number 5. Okay, so number 5 says consider the bases b1 and b2 for capital P sub 1, where you have those polynomials, right? Okay, so find the transition matrix from capital B2 to capital B1. So the goal is to find, using our notation for transition matrix, capital P sub B2 arrow B1. That's a transition matrix from basis B2 to B1. Okay, and so I'm going to take, so for B1, it helps me, sometimes it helps me to visualize things. We have basis B1 and B2. B1 is the new basis, right, because here's the new basis here, and this is the old basis. And so B2 is the old basis. So for B1, the basis vectors in B1 are P1, little p1, which is 7 plus 4x, and little p2, which is 10 plus 3x. For B2, the old basis, the basis vectors in that set are q1, which equals 3, and q2, which is equal to 6 minus 2x. Okay? So, and so now what we need to do is we need to take all of the basis vectors in the old basis and find the coordinate vectors of those old basis vectors relative to the new basis. So step 1 is find the coordinates of each old basis vector relative to the new basis. Okay? We want to find the coordinates of each old basis vector relative to the new basis. Okay? So in this case, what that means, in this case, we find the coordinates. So we want to find coordinates of each old basis vector, which is the basis vectors in basis B2, which is Q1. We want to find the coordinates of Q1 relative to the basis B1, and we want to find the coordinates of Q2 relative to the new basis also B1. Okay, so we want to find the coordinates of Q1 relative to basis B1 and the coordinates of Q2 relative to basis B1. Okay, that's step 1. And so Q1, which is equal to 3, is equal to a constant times P1, C1 times P1 plus C2 times P2. That's equal to C1 times 7 plus 4x plus C2 times 10 plus 3x. So the coordinates of Q1 relative to your new basis B1 is equal to C1 comma C2, such that C1 and C2 satisfy that equation. Q1 is equal to C1 P1 plus C2 P2. Those are the coordinates of the vector Q1 relative to basis B1. So we just have to find the solutions to this equation. So we have 3 is equal to 7C1 plus 10C2, and then we have plus 4C1x plus 3C2x. And so simplifying that, that's equal to 0x plus 3, which is equal to 4C1 plus 3C2 times x plus 7C1 plus 10C2. Okay? So we're saying this polynomial 3, which is 0x plus 3, is equal to that, which is 4C1 plus 3C2 times x plus 7C1 plus 10C2. That means that 0 equals 4C1 plus 3C2, and 3 is equal to 7C1 plus 10C2. And so what we want to do is find the solutions to the linear system 4C1 plus 3C2 is equal to 0, and 7C1 plus 10C2 is equal to 3. So we want to find all solutions C1, C2 to that linear system. And then we choose any one of them. There should only be one. Then that solution will be the coordinates of Q1 relative to basis B1. Okay, so let's do that. So let's continue to find the coordinates of Q1 relative to the new basis little b1. I mean b basis. Okay, so we're going to find the corresponding augmented matrix to that linear system, and we're going to have 4, 3, 0, 7, 10, 3. And so finding the solutions to that, I'm going to take one, I'm going to switch the rows, so I'm going to have 7, 10, 3 here, and 4, 3, 0. Actually, no. Sorry, I'm not going to do that. Never mind, I'm going to take 1/4 times the first row. So I get 1 3/4 0. And then -7 times this row and add to that one. And so I get -21/4 plus 10. And that's 19 fourths there. So I'm getting this to reduced echelon form. Okay, so I'll multiply this by, I get this, multiply the first row by 1/4, I get that. Then I'm going to take -7 times this row and add to that. And it's -7 plus 7 is 0. -7 times 3/4 is -21/4 plus 10. That's -21/4 plus 40/4, which is 19/4. Okay. Then I'm going to multiply the second row by 4/19, and I'm going to get 0, 1, 0. And I'm going to take that -3/4 times that and add to that and get that. Oh wait, there's a 3 here, sorry. 1/4, we have -7, add it there. Then I'm going to take 4/19 of that. 12/19. Okay, because then it's 1/4. Good, and that's 4/19. Good, and then, okay, but then here, so then here, when I do negative 3/4 times this and answer that and get 0, it's negative 3/4 here. And so that's negative 9/19 there. Okay, so the solution is C1 is equal to negative 9/19 and C2 is equal to 12/19. Okay, and so that should solve this linear system. And so to check, 4 times that is negative 36 plus 30, that's 0. That works. The first equation works. And the second equation is 7 times that is negative 63. Negative 63 plus 120 is 57. 57 over 19 is 3. That works. Okay, so those are the solutions. C1 is equal to negative 9/19 and C2 is equal to 12/19. So the coordinates of Q1 relative to basis B1 is equal to negative 9/19 comma 12/19. Okay, so that's the coordinates of Q1 relative to the new basis. And so next we're find the coordinates of Q2 relative to new basis. Okay, so for step 1, find the coordinates of each old basis vector relative to the new basis. This is the old basis, that's the new basis. And so we want to find the coordinates of Q2, which is the only other old basis vector, relative to the same new basis B1. And so I'm going to use the same letters here, C1 and C2. And so Q2, which is equal to 6 minus 2x, is equal to C1 times P1 plus C2 times P2. That's equal to C1 times P1, which is 7 plus 4x, plus C2 times P2, which is 10 plus 3x. And so you expand that out, and you get 7C1 plus 10C2 plus 4C1 plus 3C2 times x. Okay? So I just wrote this out as a constant plus another constant times x. So 7C1 plus 10C2 plus 4C1 plus 3C2 times x. And so that's equal to 6 minus 2x. Okay, so 6, I'm just going to write this again here. 6 minus 2x is equal to that. And so this is equal to 6, and the other thing, this is equal to negative 2. And so you get the corresponding linear system. 7C1 plus 10C2 is equal to 6, and 4C1 plus 3C2 is equal to negative 2. So that's your linear system, and the solutions to C1, C2 to that linear system are values of C1, C2 you can plug in here. So 6 minus 2x is equal to C1, P1 plus C2, P2. Then when you find C1, C2 there, C1, C2 make up the coordinates of Q2 relative to the new basis B, capital B sub 1. Okay, so let's just find C1, C2. That's the only unique C1, C2 that satisfy both the equations in that linear system. So the corresponding augmented matrix is 7, 10, 6 in the first row, and 4, 3, negative 2 in the second row. And we'll get this to reduced echelon form. So I'm going to take 1 7 times the first row, I'll get 1, 10 sevenths, 6 sevenths. And then I'm going to take negative 4 times this and answer that. And negative 40 over 7 plus 3, which is negative 19 sevenths. That's because you have 10 sevenths. You're taking negative 4 times 10 sevenths and adding it to 3. So you get negative 40 sevenths plus 21 sevenths. So negative 40 plus 21 is negative 19 over 7. And so then you're taking negative 4 times 6 sevenths, which is negative 24 over 7 plus negative 2. So negative 24 plus negative 14 is negative 38 over 7. Okay, so you get negative 38 over 7 there, because then you just do negative 4, negative 24, so negative 14 is negative 38 over 7. Okay, so negative 7/19, so I'm going to multiply the second row by. And so negative 7/19 here, then you get 2. So you get 0, 1, 2. And then just check. And so then you still have this row. So I'm going to take negative 10/7 times this row and add it to that row. I'm going to get 1, 0, and then I'm going to get negative 10/7 times 2, which is negative 20/7 plus 6/7, which is negative 14/7, which is negative 2. So now I'm going to get a negative 2 there. So C1 is negative 2 and C2 is 1. So C1 is negative 2 and C2 is 2. That's an easy solution. So you plug them into C, you get negative 14 plus 20 is 6. You get negative 8 plus 6 is negative 2. So those two work. And so the coordinates of Q2 relative to B1 is equal to C1, which is negative 2, comma C2, which is 2. Okay, so now we have the coordinates of each old basis vector relative to new basis. And so now in step 2, we just make the columns of the transition matrix those coordinate vectors. Okay, so step 2 is now P, the transition matrix from the old basis to new basis, is just the matrix whose column vectors are these vectors you got here. So the first column, you can do it in any order. The first column I'll choose negative 9/19 and 12/19. And the second column, negative 2, 2. Okay? Okay, so that's the transition matrix. So that's the answer to number 5. Find the transition matrix from B2 to B1. So I'll add the notation here. This is transition matrix from B2 to B1. Okay? That's the answer. Right, the column vectors are just, the column vectors is matrix. It's a matrix formed by the column vectors, which are these vectors we got in step 1. The coordinates of each old vector relative to new basis. The coordinates of each old basis vector relative to new basis. Okay, so that's number 5. Okay, so now next number 6. So number 6, it says find scalars C1, C2, and C3 for which the equation is satisfied. So the equation is C1 times 1, 0, negative 1 plus C2 times 2, 0, 2 plus C3 times 1, 1, 2 is equal to 20, negative 3, 3. So I guess I put that 20 in there just to make it harder. Okay, so then, so what we're gonna do is you multiply this out and add up the vectors. And so C1 plus 2C2 plus C3, comma, C3, comma, negative C1 plus 2C2 plus 2C3. So I'm multiplying each of those and combining them, and you get this, and that's equal to 20, negative 3, 3. And so that means that the first coordinate of this, C1 plus 2C2 plus C3 is equal to 20, C3 is equal to negative 3, and negative C1 plus 2C2 plus 2C3 is equal to 3. So something very convenient happens here. You just get that C3 is equal to negative 3. Okay, so we want to find all the solutions to this linear system. C1 plus 2C2 plus C3 is equal to 20. C3 is equal to negative 3. And negative C1 plus 2C2 plus 2C3 is equal to 3. Okay, so C3 is equal to negative 3. So you just plug that in. And so you get C1 plus 2C2 if you plug in minus 3 here, it's a minus 3. Move it to the other side, that's going to equal 23. Then the C3 equals negative 3, plug that in here, you get minus 6. Add the 6 here, you get equals 9. And so that'll be negative C1 plus 2C2 equals 9. And so now you have a linear system with 2 equations and 2 unknowns. And so if you add the 2 equations, this to this, you'll get 4C2 is equal to 23 plus 9, which is 32. So 4C2 is equal to 32, so C2 is equal to 8. Okay, so now C2 is equal to 8. So while C2 is equal to 8, let's just plug that into this equation. So you get C1 plus 2 times 8 equals 23. That's C1 plus 16 is equal to 23. That means C1 is equal to 7. So C1 is equal to 7, C2 is equal to 8, and C3 is equal to negative 3. And that's an answer. C1 equals 7, C2 equals 8, C3 equals negative 3. Okay? That's the only answer. There's only one answer, and that's it. Okay, so that's number 6. Okay. So after number 6 is number 7. So for number 7 is solved by Kramer's rule. Okay, so 2x plus 3y minus z is equal to 1. 4x plus y minus 3z is equal to 11. And 3x minus 2y plus 5z is equal to 21. So we want to solve this linear system by Kramer's rule. Okay, so first let's write down some information that's given to us in the problem. So using Kramer's rule, we want to know what the matrix A is for the system. A is this matrix: 2, 3, negative 1, 4, 1, negative 3, 3, negative 2, 5. That's A. The matrix A1 is the matrix where it's the same as A, except in the first column, I'm going to replace the first column with these constants here, 1, 11, and 21, right? I'm replacing the first column of A with these numbers, 1, 11, 21, and the rest of it is the same as A. A2 is the matrix that's the same as A in every column except the second column. So 2, 4, and 3 is the first column, negative 1, negative 3, 5 is the third column, and in the second column I'm going to put those numbers, 1, 11, and 21. So that's the matrix A2. And the matrix A3 is the matrix that's the same as A except for at the third column. And so the first and second columns are going to be the same. Now the third column is going to be, again, the same numbers, 1, 11, and 21 over here. Okay? So now we have the matrices A, A1, A2, and A3. And so Kramer's rule says if the determinant of A does not equal 0, then we can find the solutions x, y, and z to that linear system. X is equal to the determinant of A1 over the determinant of A. Y is equal to the determinant of A2 over the determinant of A. And z is equal to the determinant of A3 over the determinant of A. That's if the determinant of A does not equal 0, then by Kramer's rule, you can find x, y, and z by finding the determinants of these 4 matrices and plugging them into these expressions here. Okay, so let's find the determinant of A and see whether or not it's 0. If it's non-zero, we can use Kramer's rule, which we should be able to because that's what the problem tells you to do. But by finding the determinant of A, we'll need it anyway in the solution. Okay, so the determinant of A is the determinant of 2, 3, negative 1, 4, 1, negative 3, 3, negative 2, and 5. So I feel it's important to point out that the determinant of this matrix should be non-zero in order to use the rule. Even though the question tells you to use it, it's good to know that Kramer's rule depends on that piece of information. Because if finding the determinant of A, we can find the cofactor expansion along the first row. Again, I'll just go with that. Minus 3 times the determinants of this submatrix plus negative 1 times determinant of that submatrix. So 2 times that minus 3 times that plus negative 1 times that. And so that's equal to 2 times 5 minus 6, which is negative 1, minus 3 times 20 minus negative 9, which is 29, plus negative 1, which is minus 1 times negative 8 minus 2, which is negative 11. And so this is equal to negative 2 minus 3 times 29, which is 87. That's minus 87. And then minus 1 times negative 11, which is plus 11. And so then this is minus 89 plus 11, which is minus 78. Wait, no, sorry. These are all negatives here. It's negative 2 minus 87 plus 11. Plus 11, which is minus 89 minus 78. Okay, so the determinant of A is minus 78. Okay, the determinant of A is negative 78. And so you have a negative 78 in the denominator for each of them. So now we just need to find the determinants of A1, A2, and A3 and then plug them in to the numerators here, and then we found the answers to what X, Y, and Z are, the solutions to the original linear system there. Okay, so it's, right, okay, determinant A is non-zero, so you can use Kramer's rule, just like I said. Okay, so now, what's the determinant of A1? What is the determinant of that matrix? The determinant of A1 is equal to the determinant of that. So you just write this out. This is equal to 1 times the determinant of that submatrix minus 3 times the determinant of that submatrix plus negative 1, just minus 1 times the determinant of that submatrix. Okay, what do we get? Okay, and so calculating this, you get 5 minus 6, which is negative 1, minus 3 times 55 plus 63. 55 plus 63 is 118. Okay, and then you have negative 22 minus 21, which is negative 43 times negative 1 is plus 43. So let me just check. 55 plus 63 is 118. Okay, so then 5 minus 6, negative 1, negative 22 minus 21, negative 43. And then times 1 is plus. That's a plus there. Just write that. Okay, that's clear. This is negative 1 minus 3 times 118, which is minus 354 plus 43. You're allowed your calculator, so you can just plug this stuff in. So you have negative 311, negative 312. Okay, so the determinant of A1 is negative 312. So the determinant of A1 is negative 312. So I just plugged in that in there. That's negative 312. So negative 312 over negative 78 is 4. So x is equal to 4. So actually, this works out quite nicely. Negative 312 over negative 78 is 4. 7 times 4 is 28, 280. 8 times 4 is 32. 280 plus 32 is 312. Okay, so x is 4. So now we'll find the determinant of A2. Now we're going to find the determinant of A2. And that's equal to the determinant of that matrix, which is 2, 1, negative 1, 4, 11, negative 3, 3, 21, 5. And so we find the cofactor expansion on the first row. It's 2 times the determinant of that submatrix minus 1 times the determinant of minus 1 times the determinant of that matrix plus negative 1 or minus 1 times the determinant of so now this is equal to 2 times the determinant of that, which is 55 plus 63, which is 118 again. So that's 2 times 118. Just check 63 plus 55, 18 plus 100, which is 118. Good, 2 times 118. Minus 20 minus negative 9 is 29. 29, so it's minus 29. 84 minus 33, which is 51, so minus 51. Okay, so this is just arithmetic. Don't give up. Okay, so it's 84 minus 33, which is 51. So negative 1 times 51, negative 51. And so this is 2 times 118, which is 236 minus 29 minus 51. And so minus 29 minus 51 is minus 80. So 236 minus 80 is 156. So that's 156. Okay, so 156 over negative 78 is negative 2, so y is negative 2. Okay, 156 over 78 is 2, but then it's 156 over negative 78, so you get negative 2. Okay, 7 times 2 is 14, 8 times 2 is 16, so you get 156 there. Okay, so then in terms of A3 is so in terms of A3 is the determinant of 2, 3, 1, 4, 1, 11, 3, negative 2, 21. So in terms of that, you find the cofactor expansion along the first row. That's 2 times the determinant of 1, 11, negative 2, 21, minus 3 times the determinant of 4, 11, 3, 21, plus 1 times the determinant of 4, 1, 3, negative 2. Okay, so you find the determinant of that. You find all that. So let me just check to make sure this is perfect. Okay, so now in terms of this submatrix is 21 plus 22, which is 43. 43 times 2 is 86. That's 86. And then 4 times 21, 84 minus 33 is 51 times 3, which is 153, so that's minus 153. And then negative 8 minus 3 is negative 11, and so that's minus 11 there. And so then you get negative 60, so negative 78 there. So the determinant of A3 is negative 78, which looks perfect because if I plug negative 78 in here, I get z is equal to negative 78 over negative 78, which is 1. And so z is 1. Okay. And so x is 4, y is negative 2, and z is 1. And we found that solution using Kramer's rule. Since the determinant of the coefficient matrix is non-zero, that implies that by Kramer's rule, these are the solutions x, y, and z for that linear system. Just that one solution. X is 4, y is negative 2, and z is 1. Okay, so that's number 7. Number 8. So 8, let R2 have the weighted Euclidean inner product. Okay, we have the weighted Euclidean inner product 3u1 v1 plus 5u2 v2. Okay, so we have that. And we have u, v, and w, and k written down there. Okay, I guess I'll write this. U is the vector 2, 2. V is the vector 4, 1. W is that vector, and K is equal to 7. U, V, W. Okay, 7. Compute the state quantities. So for A, part A, it says find the inner product of K, V, and W using that. So that means that it's the inner product of K, which is 7, 7V, which is 7 times 4 comma 1, and the vector W, which is 0 comma negative 1. That's the inner product of the vector 28 comma 7 and 0 comma negative 1. Okay, so what is the inner product of those two, of this and this? Well, it's 3 times the first component of the first vector times the first component of the second vector plus 5 times the second component of the first vector times the second component of the second vector. This is times 0, so this is 0 plus 7 times 5 is 35, minus 1 is negative 35. So this is 0 minus 35, which is negative 35. So the inner product of K, V, and W here is negative 35, using that weighted Euclidean inner product and that U, V, W, and K. So that's A. B. What is the norm of U? Well, the norm of U is the square root of the inner product of U with itself. Okay? By definition. And so what that's equal to is the square root of the inner product of U with itself. That's 3 times the first component of U, which is 2, times the first component of U also, which is also 2, plus 5 times the first component times the second component of U, which is 2, times the second component of that U, which is also 2. And so then that's equal to the square root of the sum of the squares of those products. That's 12 plus 20, that's 32, so this is the square root of 32. Okay, so the norm of U is the square root of 32. C, the distance between C, the distance between U and W is equal to the norm of U minus W. Well, the norm of U minus W is just the square root of the inner product of U minus W with itself. Okay, and so so what is U minus W? We're going to decide. So U minus W is that vector U, 2 comma 2, minus that vector W, 0 comma negative 1. So that's 2 minus 0, which is 2, comma 2 minus negative 1, which is 2 plus 1, which is 3. And so you get U minus W is 2 comma 3. Okay, so this is the square root of the inner product of 2 comma 3 with itself, 2 comma 3. Okay, so then, so 3 times, the inner product of that with itself is 3 times the first coordinate of this vector, which is 2, times the first coordinate of itself, which is still 2, plus 5 times 3 times 3. So that's equal to the square root of 12 plus 45, which is 57. So that's the square root of 57. Okay? Okay, so you have 12 plus, again, 45, which is 57. So the distance between U and W is the square root of 57. Okay, and then D, we want to find the inner product of U plus V and W. So we want to. So what's U plus V and what's W? U, we already know what W is. U plus V is U, which is 2 comma 2, plus V, which is 4 comma 1. And so 2 comma 2 plus 4 comma 1 is 6 comma 3. So U plus V is 6 comma 3. So this is the inner product of 6 comma 3 and W, which is 0 comma negative 1. And so by that definition of the weighted inner product, we get, for this example, this is 3 times 6 times 0 plus 5 times 3 times negative 1. So So that's 0 minus 15, that's negative 15. So the final answer is negative 15 for D. So A is the square root of, A is negative 35, B is the square root of 32, C is the square root of 57, and D is negative 15. And that is number 8. Okay. Okay, so that's number 8. So number 9, okay, so for number 9, determine whether B is in the column space of A, and if so, express B as a linear combination of the column vectors of A. Okay, so I guess I know. Okay, so A is equal to 1. The first column is 1, 0, 1, 0. The second column is 2, 1, 2, 1. Third column is 0, 2, 1, 2. And the third column is 1, 1, 3, 2. That's in matrix A. The matrix B is the column vector 4, 3, 5, 7. Okay, so we want to determine whether this B is in the column space of A, and if so, express B as a linear combination of the column vectors of A. So let's call the first column of A C1, the second column of A C2, the third column of A C3, and the fourth column of A C4. Okay? So the question is are there values, k values, such that k1 c1 plus k2 c2 plus k3 c3 plus k4 c4 is equal to b, where the k's are scalars. So k1, k2, k3, and k4 are assumed to be scalars. Okay, so are there values for k1, k2, k3, k4 scalars, such that that linear combination is equal to B? So what that would mean is that K1 times 1, 0, 1, 0 plus K2 times 2, 1, 2, 1 plus K3 times 0, 2, 1, 2 plus K4 times 1, 1, 3, 2. And that's equal, can that equal 4, 3, 5, 7? Okay. This is a linear combination of the column vectors of A, and we're setting it equal to B, and so we're trying to find whether or not we can plug in values, numbers for K1, K2, K3, K4, such that this equation is true. So if you look at the entries here, you get the linear system K1 plus 2K2 plus 0K3 plus 1K4 is equal to 4. You get K2, 0K1 plus 1K2 plus 2K3 plus 1K4 is equal to 3. You get K1 plus 2K2 plus K3 plus 3K4 is equal to 5. K2 plus 2K3 plus 2K4 is equal to 7. Okay? So if you take K1 plus 2K2 plus K4, it should equal 4. If you take K1, looking to get those equations there. Okay, and then K2 plus 2K3 plus K4 is equal to 3. K1 plus 2K2 plus K3 plus 3K4 is equal to 5. And K2 plus 2K3 plus... Okay, so then, I wrote this out here for you. I'm going to have to erase it so I have room. So what I'm going to do now is I'm going to find the solutions to this linear system. That'll be values of, that'll be values of K1, K2, K3, and K4 since this equation holds, and that would express the columns of A as a linear combination. Express B as a linear combination of the column vectors of A. Does that make sense? Okay. So I'm going to find those K's now, and you just plug them there. Okay, so I'm going to erase this. so now I'm going to find the solutions to that linear system. I'm first going to write its corresponding augmented matrix 1, 2, 0, 1, 4, 0, 1, 2, 1, 3, 1, 2, 1, 3, 5, 0, 1, 2, 2, 7. Okay, so the first row I'm going to keep the same. The second row I'm going to keep the same for now. The third row I'm going to take negative 1 times the first row and add to the third row, because I'm using Gauss-Jordan elimination. You get 0, 0, 1, 2, 1. And then this row I'm going to take negative 1 times the second row and add to the fourth one. I'm going to get 0, 0, 1, 0, 0, 0, 1, 4. Okay, and so this won't be too bad. Then the last row is going to the last row we're done. The next we're going to take negative 1 times the last row and add to the third row. Get 0, 0, 1. Get negative 2 times this row and add to that one, and we're going to get negative 7 there. And then I'm going to take, after you have this row and this row, I'm going to take negative 2 times this row and add to that, and negative 1 times this row and add to that. And so we get 0, 1, 0, 0. And so we get 14. We add 14 to 3, and we add negative 4 to 3. So we add 10 to 3, and we get 13 here. And so okay, and so then the last thing I'm going to write the top row again, make things a little easier for me, and then the last row is going to be 0, 0, 0, 1, 4, 0, 0, 1, 0, negative 7. Okay, so then, so I'm going to take the last row, multiply it by negative 1, and add it to this one. And so then I'm going to get 1, 2, 0, 0. Okay, so then, okay. And then I'm just going to take negative 1 times the second row, negative 2 times the second row into the first one. And so this is going to be 0, 0, 0, 1, 4. 0, 0, 1, 0, negative 7, 0, 1, 0, 0, 13, negative 2 times this and add to that, negative 26 there. Okay, so I got to reduce for echelon form. And so the solution we get is K1 is negative 26, K2 is 13, K3 is equal to negative 7, and K4 is equal to 4. So that's, I don't think you can guess that. I think you need to solve it. So K1 is negative 26, K2 is 13, K3 is negative 7, and K4 is 4. If you can guess that, then you're going to have to tell me how you did that. Okay, so then those are the values of K. Okay, and so then just negative 26 times the first column plus 13 times the second column plus negative 7 times the third column plus 4 times the fourth column equals B. And that's how you express B as a linear combination of the column vectors of A. And so by doing that, you show it can be done, and you do it. So that answers number 9. Okay? So that's number 9. And so the last problem on this practice final is number 10. So number 10, determine whether T is a matrix transformation and justify your answer. So here we have T of x comma y is equal to 2x minus 3y comma x minus y. Okay? So that's t. And so we want to determine whether t is a matrix transformation, just for your answer. So if we can show that t is a linear transformation, that means it's also a matrix transformation. Okay? Because every linear transformation is also a matrix transformation. Okay? So let's do that. So in order for it to be a linear transformation, it needs to have the homogeneity property, which is t of k times x comma y is equal to k times t of x comma y. It also needs to have the additive property that t of x comma y plus x prime comma y prime. I'll write this here. T of x comma y plus x prime comma y prime is equal to t of x comma y plus t of x prime comma y prime. Okay, this is called the homogeneity property, this is called the additive property. Those two properties together means that means you have linear transformation, and if something's a linear transformation, it is also a matrix transformation. Okay, so t of k of x comma y, that would be t of the vector kx comma ky. Well, by the way t is defined, that would be 2 times x, but that would be 2 times kx minus 3 times ky, comma, kx minus ky. That would be equal to, if I factor out the k, it would be k times 2x minus 3y, comma, x minus y. Well, what's this? This is just t of x comma y, so this is k times t of x comma y. So I just showed is that t of k of x comma y is equal to k times t of x comma y. So I proved the homogeneity property for t. Okay, so t of x comma y plus x prime comma y prime is t of x plus x prime comma y plus y prime. And so this is equal to t of okay, so it's all right here. T of x comma y plus x prime comma y prime is equal to t of x plus x prime comma y plus y prime. And so what that's equal to is by this, it's equal to 2 times x plus x prime minus 3 times y plus y prime, comma, x plus x prime minus y plus y prime. Okay. And what that's equal to is 2x plus 2x prime minus 3y minus 3y prime, comma, x plus y just write it this way, x plus x prime minus y, and then carrying out the negative sign minus y prime. Okay, well that is equal to let me put this over here. That is equal to 2x minus 3y, comma, x minus y, plus 2x prime minus 3y prime, comma, x prime minus y prime. Okay, so if you take this part, 2x minus 3y, and then 2x prime minus 3y prime, you separate them into the first quadrant of this vector and this one, and you add them. And then you take the x minus y here, and you put that here in the second quadrant, and you take the x prime minus y prime and put that there. Then what you get is t of x comma y plus t of x prime comma y prime. This is t of x comma y plus t of x prime comma y prime. Okay, so what I showed is that t of x comma y plus x prime comma y prime is equal to t of x comma y plus t of x prime comma y prime. And now I proved the additive property for t. And so since I proved the homogeneous property and additive property for t, it's a linear transformation, which means it's also a matrix transformation. Okay, and so that is number 10. And so that is the test, and we're done. Okay, so hopefully if you could do all 10 of these problems yourself, that means that you're on track to doing well on the final. If you can't answer these questions on your own, you should go over this video, understand how to do these problems, so that when you see a problem like this on the exam, you could then do it applying the techniques and methods that I applied in this video to your problem on the test, okay? But it's not just these type of problems that are on the test, right? Anything we covered in the class of the semester, that type of question could be on the final. So you need to be ready and know everything, all the material we covered for the semester, okay? So good luck studying and good luck on the final.